Okay, so we're recording now. So right, lesson 1 is the early atomic theories and how these were the origins of quantum theory that led to our current model of the atom. So the atom is the smallest unit of an element. It has all the chemical properties of that element. And here we are going to cover the various theories that led to this current model of the atom in sort of a historical way, and talking about the significance of each one of these models as stepping stones towards our current model of the atom. So when we talk about matter, really matter is anything that has mass and takes up space. This means everything around you, including ourselves, is matter. And matter is made up of tiny particles called atoms. Now, back in early Greek philosophers described matter as being made up of tiny, indivisible particles that in Greek they called atomos. And atomos means indivisible or uncuttable. So it's basically the most fundamental indivisible particle that these Greek philosophers could think of. They imagined that that's what matter is made out of. Now, today, scientists, we are able to see individual atoms through special microscope called the scanning tunneling microscope. But before the invention of this scanning tunneling microscope, and before us being able to visualize matter at the atomic level, scientists could only speculate about that matter consisted of atoms. Here I've got an image of STM image of atoms on the surface of graphite. Graphite is a form of carbon, and each of these peaks you can see represents atoms of carbon all lined up in a very orderly grid, which is what the arrangement of carbon is in graphite. So when this early Greek philosopher first suggested atoms, his ideas were just based on intuition and reasoning. There was no experimentation. And then as experimentation and the scientific method gained importance, that's when the model of the atom began to develop and evolve. So let's take a look at some of the key scientists that were involved in this atomic model development. So the first scientist we can look back at was John Dalton, who was actually a school teacher. And he came up with his model of the atom based on the experiments of other scientists that were doing experiments. And his atomic theory consisted of a few major points here. And he thought that all matter was composed of tiny particles called atoms. So drawing on what Democritus had said many years before. And that atoms could not be divided or changed into one another. Atoms cannot be created or destroyed. All atoms of one element are the same in shape, size, mass, and all other properties. All atoms of one element are different in these properties from atoms of other elements. And chemical change is the union or separation of atoms, bringing together of atoms in different combinations or separating them. And in these unions and separations would be in whole number ratios, such as 1:1 or 1:2, 2:3, etc. And so this model of the atom, Dalton's model, became known as the billiard ball. It didn't account for subatomic particles like protons and neutrons and electrons that we are aware of today. Back in Dalton's day, this round billiard ball looking thing was pretty much all they knew about atoms. Here on the left side of the screen, I've got just a pictographic representation of Dalton's atomic theory that might work better for you. It explains all the other points that I talked about here with some added pictures. For example, all atoms of a given element. So if you look at oxygen, all oxygen atoms would be similar to each other. Nitrogen atoms would be different from oxygen atoms, but all nitrogen atoms would be similar to all other nitrogen atoms, and that you cannot interconvert oxygen and nitrogen atoms, and that you can form these compounds in whole number ratios to these elements to produce compounds, such as one nitrogen and one oxygen can make nitrogen oxide here compound. So after John Dalton, to understand the structure of the atom better, many years later, a scientist named J.J. Thomson, he was doing experiments that applied high voltage to partially evacuated tubes with metal electrodes at each end. So here is a picture showing these evacuated tubes, and there's electrodes at each end. There's a negative and a positive. And he observed that a ray was produced that started from the negative electrode and traveled to the positive electrode, or the cathode. He also, from the negative electrode cathode to the positive electrode anode. He also looked at the deflection of these rays, which he called cathode rays, by electricity or magnetic fields. So here in this picture, for example, you can see, and I hope it's big enough, I will actually stretch it out bigger for you to be able to see that here is that cathode ray, and a magnet is able to deflect it, is able to pull it up and attract it. So he studied this phenomenon, and he observed that the negative pole of an electric field was able to repel the ray. So he explained his observations by hypothesizing that the ray must be composed of a stream of negatively charged particles, which we now know to be electrons. And his results suggested that the atom, after all, was not the smallest unit of matter, and there were subatomic particles within the atom. So he discovered the presence of electrons. So this is one step further into our understanding of the atom, and changing the model and refining it further. And since all electrons could be produced from electrodes made from different metals, so he tested this with different metals, and so therefore all atoms must contain these electrons. It wasn't anything unique to a certain type of metal. All different types of metals, it seemed, had this ability and did contain electrons. And from this, he postulated that since atoms themselves are electrically neutral, so therefore, if they have this negative charge, they must also contain a positive charge, so that the negative and the positive cancel each other to produce a neutral atom. And so he came up with being able to figure out a charge to mass ratio of the electron, which is noted here. And J.J. Thomson also proposed that the atom is a sphere of uniform positive charges in which negative electrons are embedded. So here is a picture of this model here. So the blue fog is the blue sphere is a sphere cloud of positive charge, and then embedded in it are these negative electrons. And this model is sometimes called the raisin bun model, because it kind of reminds people can think of it in terms of a bun with raisins dotted all throughout it, or a blueberry muffin, or a plum pudding. There's various names given to this very basic model of J.J. Thomson's, or chocolate chip cookie model, where the electrons represent and are analogous to the negatively charged electrons, the blueberries, the raisins, the chocolate chips, the what have you. Those are dotted throughout the atom, and those carry the negative charges that are just distributed and embedded into this positive charge of the atom. Then a few years later, a scientist called Robert Millikan, he discovered the mass of the electron, and he used charged oil drops to determine the charge of the electron. And here is a schematic showing the setup of his experiment. So he used an atomizer to produce oil droplets, very fine oil droplets, which he then sent through electrically charged plates. And as they went through the X-rays, he blasted them with X-rays. And the X-rays produced charges on these droplets. And he discovered that he could stop the falling of these oil droplets by gravity just by adjusting the voltage across these two charged plates. And from that, he calculated the charge on the oil drop from the voltage and the mass of the oil drop. And he used this charge to mass ratio that was determined by Thomson previously. And he used that ratio to then calculate the mass of an electron. So then at this point, then there was an understanding that the atom was not the smallest, most indivisible particle, that it had actually had electrons, that these electrons had a mass. And that's what Robert Millikan discovered in 1909. And soon after, Ernest Rutherford, who was another scientist, he was doing a series of experiments involving different types of radiation, alpha particles, beta particles, and gamma rays. And he was working with radium, which gives off 3 different types of radiation, the alpha, beta, and gamma. Now, alpha particles are helium nuclei. They're made out of 2 protons and 2 neutrons. And using these principles, he devised an experiment, which is very famous now. It's called his gold foil experiment, which was set up kind of like that. There was a source that produced alpha particles. So there was a beam of alpha particles being shot through towards a very thin gold foil. And he hypothesized that if Thomson's model was accurate, that these massive alpha particles, which are made out of the protons of the helium nuclei, should break through the thin foil. Now, at this time, they didn't know about protons and neutrons, but he knew that these alpha particles were quite massive and that they should be able to break through the thin gold foil, almost like bullets going through tissue paper, and that they should only be minor deflections. They shouldn't really be reflected or deflected back, that they should be going pretty much straight through, kind of like what this picture is showing. This is Thomson's model. And so Rutherford thought that if this model is correct, most of these alpha rays should be going straight through. But the results that he got from this gold foil experiment were very different, shockingly different. So most of these alpha particles passed straight through the gold foil, but some of them were deflected at different angles. So here in this diagram, it's showing that some of them are deflected and towards the detector. So not all of them went straight through. Some of them got bent away. And then to his great surprise, some of these reflected straight back towards the source, never reaching the detector. Some of these bounced straight right back. And that was a huge surprise. And by looking at these results, he concluded that the deflection of these alpha particles must be caused by some concentrated positive charge at the center of the atom that contains most of the mass of the atom, that there must be something quite massive and quite dense at this very center of the atom to cause the deflection of and even reflection back towards the source of these alpha particles. And from this, he proposed a planetary or a beehive model, where he proposed that the atom has a dense, positively charged atomic center called a nucleus. And most of the atom, he proposed, is empty space, and the electrons move around the nucleus at relatively far distance, similar to kind of planets orbiting around the sun. or bees buzzing around a beehive. So this was Rutherford's model was referred to as the planetary model or the beehive model. And he named this positive charges of the nucleus protons. So this was Ernest Rutherford's important contribution, this gold foil experiment, which led to the understanding of the presence of the nucleus and the presence of protons, positively charged center in the nucleus of protons. So to further develop this atomic model, there were some limits to this model that Rutherford proposed. So after his discovery, generally scientists were tempted to think of atoms as these microscopic solar systems. It kind of made sense, just like the way the planets orbit the sun in circular paths. It seemed very reasonable that these electrons should be orbiting the nucleus. Well, the problem with this model of Rutherford's was that, according to the laws of classical physics, you would predict that electrons would continuously be losing their energy and then spiraling towards the nucleus and crashing into the nucleus. But this was not what was observed. This was not consistent with real world observations. Generally, most atoms are stable. They don't appear to be collapsing. So this suggested that although the electrons are constantly moving, they don't lose energy. And so Rutherford's model was not able to explain the stability that was observed with atoms. So there was more work to be done. And more scientists continued to probe the nature of the atom and to further refine this model. Now let's talk about light for a minute, because that was another important area where a lot of research was being done, was to discover the nature of light. Now, light or light energy is electromagnetic radiation. We understand that today. Visible light is just the portion of the spectrum that can be seen by the human eye. Here is the electromagnetic spectrum, and this is the section that's occupied by visible light. But there are radio waves, microwave rays, infrared rays, X-rays, UV, cosmic rays, gamma rays. These are all part of this continuum of the electromagnetic spectrum, a very small section of which is visible light. So back in the 1600s, a scientist named Christian Huygens, he conducted some experiments that led him to a theory that light is a wave. And at the time, not all scientists agreed with him. For example, Isaac Newton believed that light was composed of little tiny particles, which he called corpuscles. And so investigations continued, and new evidence from experiments with refraction, diffraction, reflection, which I'm sure you all have studied in physics in earlier years, they provided a great deal of support for this wave hypothesis that was being proposed by Huygens. But some 200 years later, in the mid-1800s, James Maxwell, he proposed a theory regarding the properties of magnetism, light, and electricity. And he theorized that light could act on charged particles because it existed as an electromagnetic wave made out of magnetic and electric fields. Now, over time, Maxwell's electromagnetic theory gained wide acceptance and came to be known as the classical theory of light. According to Maxwell's theory, light is an electromagnetic wave, and it's composed of continuous wavelengths that form this electromagnetic spectrum. So that covers what was the understanding of light, the classical theories of light. Now, although this wave model of the light explained many aspects of its behavior, this model couldn't explain many phenomena. There was many experiments that could not be explained by this wave property of light. And there's three actually very important experiments that are key to our understanding of how this electromagnetic radiations and atoms interact together. And these experiments led to the development of the idea of quantized energy and photons. Now, these are, I've numbered the three, and we will be covering them in the following slides. So the first experiment, the first phenomenon that was not explainable by the wave model was the emission spectra generated. So when you get light emitted from electronically excited gas atoms, this could not be explained by the wave model. Also, emission of electrons from metal surfaces. This was called the photoelectric effect. So there is shining light on a metal surface emitted electrons, and this was not able to be explained by the wave model of light. And finally, black body radiation, the emission of light from hot objects. This was also not explainable by the wave model. And so to account for the observed behavior of light and atoms, so the physicists had to develop a completely new way of thinking about this, and this was called quantum theory. And this was a new form of physics, and this new form of physics more accurately explains the behavior of light and matter. So let's go through these three phenomenons, emission spectra, photoelectric effect, and black body radiation, and see how they contributed to the further development of our modern model of the atom. So in the mid to late 1800s, there was a couple of scientists called Bunsen and Kirchhoff, and also other scientists, and they were doing experiments with spectroscopy, and they showed that each element could produce its own unique line spectrum. I have some definitions down here that cover what is spectroscopy, continuous spectrum, and emission spectrum. But the line spectrum, essentially, so let's talk about what is spectroscopy first of all. Spectroscopy is the analysis of the spectrum that's generated to determine the properties of the source that produces the spectrum. So in spectroscopy, light, so here I can show you in this diagram, light passes through a sample and then it's dispersed by a prism, and the dispersed light forms a spectrum. Now, if this is a continuous spectrum, if the emission contains all wavelengths, in this case, if the source is a solid light source, white light, and it passes through the prism, you will see all wavelengths of light on the detector. If you have an emission spectrum of the electromagnetic radiation emitted from an atom when it's excited and then returned to a lower energy state from a higher energy state. So for example, here you have a high voltage applied across a tube containing hydrogen gas. So this is a hydrogen gas discharge tube. That's what this is called. So if you apply high voltage across a tube containing hydrogen gas and pass that light through a very fine slit and through a prism, you get a separation and you get this very unique line spectrum. The line spectrum is the emission spectrum that contains only those wavelengths that are characteristic of that element being studied. It's almost like a fingerprint, a unique fingerprint to that element, if you will. So if you compare and contrast these two spectra, you can see here you have the full spectrum. Here only you have very discrete wavelengths that are present, that are unique to hydrogen. And so from this, quickly, scientists got very excited and they began to quickly catalog the line spectrum of all of the elements that were available to them at the time. And they could see that each element really had its own unique fingerprint of a set of lines at very discrete wavelengths. And this unique line spectrum of the hydrogen atom is actually very important to atomic theory, because it interested a scientist called Niels Bohr, and Niels Bohr went to further develop atomic theory. So yeah. Sorry, 1 second. I'm just trying to see, somebody is trying to get into the meeting. I'm sorry for.
Yeah, that's me. It's because my mic is having issues. I'm trying to join on my phone.
Okay, so do you want me to let you in, or is that?
Yeah, and then
Yeah,
I'll
okay,
leave
okay.
from
All
my
right.
computer.
Sure, okay. All right, so yeah, we will talk a little bit more about Niels Bohr's atomic theory, but essentially he had to make some assumptions about the classical laws of physics that were inadequate, completely inadequate to describe atoms, and he used the idea that energy must be quantized, and we are going to look at this later. So then the second phenomenon that we were going to talk about, the photoelectric effect, this was something that was initially discovered by a scientist called Heinrich Hertz in 1888. And he discovered that when he would shine light on metal surfaces, it caused the emission of electrons from the metal. And he reported this photoelectric effect, but he couldn't explain it. And this accidental discovery of his had a major impact on classical theories of light and matter. So according to classical theories of light that we discussed earlier in another slide, the intensity, the brightness of the light shining on the metal should be what determines the energy of the electrons emitted. But instead, in Hertz's experiments, he discovered that it was the frequency of the light that was more important in determining the energy of these emitted electrons. So that low frequency light did not emit electrons, but at certain high frequency lights, you were able to get electrons emitted from a metal surface. And since the classical theory of light and matter could not explain these observations, it was actually viewed as a flawed observation, a flawed experiment, and it kind of sat on the shelf, and it didn't go really any further. You have to keep in mind that back in the late 1800s, matter and energy were considered to be very distinct, unrelated things. Matter was thought to be composed of particles and mass, and to occupy a certain position in space at a particular time, whereas light energy was considered to be electromagnetic waves. It had no mass, it had no specific position in space. Now later, Einstein was able to explain this photoelectric effect, and he received the Nobel Prize for his experimentation, and we will discuss this in another slide coming up. So this was actually, although at the time it wasn't explained and it was viewed as flawed, this was very important to the development of modern theory of atoms and light. The third key phenomenon that was important, that could not be explained by classical physics, was black body radiation. In black body radiation, there was a scientist called Max Planck, and in 1900, he was studying the spectra of the radiant energy, so the energy of the electromagnetic waves that gets emitted by a solid body called black bodies that were heated to incandescence. So if something is made so hot that it starts to glow, so he was studying what kind of spectra these glowing black bodies emit. And he studied the light emitted by these hot objects. And he discovered that, here I'll show you in this graph, for example, that a red hot object, as opposed to a white hot object, emitted light of different colors and intensities, and that the light emitted did not follow the expected results of classical theory of light. In classical theory of light, it was expected that the intensity would go up with the energy. As the energy increased, so would the intensity. But what he was observing is that no, there was distinct curves and distinct behavior for red hot and white hot light. So these unexpected results of these heating experiments led Planck to hypothesize that this must mean that matter can only gain or lose energy in whole number multiples according to this kind of an equation, E is equal to NF, where N was some integer, F is the frequency of the radiation, and H is the famous Planck's constant. And from that, we get Planck's quantum theory. And in Planck's quantum theory, energy can only be gained or released in chunks of some minimum size, which he termed quanta. And for his work, Planck received the Nobel Prize for the discovery of energy quanta and his quantum theory. So a quantum is defined as a unit or a packet of energy. And if the idea of sort of a packet of energies, chunks of energy is not very intuitive, you can think of it in terms of somebody climbing a stairs versus somebody climbing a ramp. If somebody's climbing up a ramp, their potential energy of this person walking up the ramp increases uniformly in a continuous manner as they're going up. But in a quantized manner, their energy would be equivalent to going up with each step. At every step, there's a finite increase in their energy level. So you can think of it in this way, that energy is gained or released in quanta, in chunks, in packets of energy. So finally, in 1905, Albert Einstein took the photoelectric effect that Heinrich Hertz discovered back in 1887 and was not able to explain. And Albert Einstein, a few years after Planck had presented his quantum theory and scientists began to see its applicability to so many different experimental observations, Einstein explained this photoelectric effect by applying Planck's idea of a quantum of energy. And he received a Nobel Prize for this work, for this explanation in 1921. So in the photoelectric effect, he explained, electrons are emitted by matter that absorbs energy from shortwave electromagnetic radiations from visible or UV light. And Einstein suggested that these electromagnetic radiations could be viewed as a stream of particles called photons. So a photon is a unit of light. So here we have low frequency energy that is not causing the emission of photon, or high energy frequency that is causing the emission of electrons. And so he proposed that electrons were emitted from surfaces of metals because a photon collided with the electron. And during this collision, the energy of the photon transferred to the electron, and that some of the energy, the transferred energy, would cause the electron to break free from the atom, and the rest would be converted to kinetic energy. Now, to free an electron from an atom requires the energy from a minimum of 1 photon. And in the case where an electron stays in place, it stays in place because of electrostatic forces. If a single electron absorbs a single photon with the right quantity of energy, then the electron can escape the metal surface. And if the photon doesn't have enough energy, then no electron can escape the metal surface, no matter how many photons strike it. If they don't have the right amount of energy, it doesn't matter how many you fire at it, no electrons are gonna escape. And that the kinetic energy of the ejected electron would depend on the frequency of the light used. And when a frequency was below a certain level, called the threshold frequency, no electrons are ejected. And that was Albert Einstein applying Planck's quantum theory to explain the photoelectric effect, and earned himself a sweet Nobel Prize. So soon after that, then Bohr used also Planck's idea of quantized energy. And so if you remember, we were talking back a few slides ago about the atomic spectra, and that Bohr used Planck's discovery of quantized energy to help explain the emission line spectrum of the hydrogen atom. So he assumed that classical physics was completely inadequate to describe atoms, and by applying Planck's idea that that energy is quantized, he developed a quantum model for the hydrogen atom. And this model had to account for the experimental evidence that was provided by spectroscopy that showed electrons could have only particular discrete energy levels, and you could only see certain frequencies here. So let's go back to Bohr's model. In Bohr's model, he proposed the idea of energy levels and orbits in the atom. So in his model, he proposed that electrons would move only in specific orbits around the nucleus. So here we have got a model of Bohr's atom. Here's the nucleus. And then there's these orbits of specific energy levels all around the nucleus. And this is where the electrons would travel. Each of these would have a specific energy level. So here in an energy level diagram, for example, you could see that the first orbit would have the lowest energy, and then the energy levels of each subsequent orbit would be different. And the energy level of the orbit increased as its distance grew greater from the nucleus. And that an electron would gain more energy as it becomes more excited, and it would move into an orbit that was farther away from the nucleus. And that you would get these particular wavelengths of light emitted by electrons of the hydrogen atom by changes in the energy. So when an excited electron in the hydrogen atom moved to a lower G energy level, it would emit a photon of light. And this is true of excited electrons in all other atoms as well. So for example, if an excited electron moved from the 6th orbit down to the 2nd orbit, it would produce photons of light that would have a wavelength corresponding to this purple line on the spectrum. And so same for the blue, the green, and the red. So that's how you would get these discrete wavelengths of light corresponding to electrons in the excited state, moving to a lower energy level and emitting photons of light. So although this model was later shown to actually be incorrect, Niels Bohr received the Nobel Prize in Physics in 1922 for the development of the quantum model of the hydrogen atom. So this was although this model is very simplistic and it's not entirely correct, it was a very important stepping stone towards the understanding of the atom, and it was the first suggestion that the atom, there was a quantized energy levels in the atom. So that was the main important thing, that the energy of the electron of the hydrogen atom was quantized. That was what was very important about Bohr's contribution to the atomic model. But what Bohr's atomic model did not explain is that why electrons behaved in this way, but his model was consistent with the observed line spectrum of the hydrogen atom, and it was consistent with Planck's quantum theory. So just to go over Bohr's model again in a little bit more detail, it had its successes, it had its failures, but first it proposed that the electron of the hydrogen atom moved about the nucleus in a circular orbit, and that only orbits of certain radii corresponding to certain energies were permitted. This is what we were showing here in these diagrams. And these are the discrete energy levels of the radii where the electrons moved. And then an electron in a permitted orbit is said to be in an allowed energy state, and that an electron in an allowed energy state would not be spiraling and falling into the nucleus, as was the problem with Rutherford's model. And the second thing this Bohr's model suggested was that the electron can change from one allowed energy state to another one. So from one allowed energy state up to another one, not anywhere in between. This is the idea of the quantized energies of the electrons. And that it could do this either by absorbing or emitting radiant energy, the frequency of which would have to correspond exactly to the energy difference between the two allowed energy states. So if it absorbed the right amount of energy, then it could get excited to a higher energy level, or if it emitted the right amount of energy, it would be emitting that energy and coming down to a lower energy level. And these were the allowed energy levels. This is how energy levels are quantized in Bohr's model of the atom. So each one of these orbits was assigned an integer n, which is known as the principal quantum number, and n can be 1, 2, 3, and so on. The larger the value of n, the farther the electron is from the nucleus. And that the lowest energy state is that for which n is equal to 1. So going back to this slide, n is equal to 1. Here's the lowest energy state. And as it goes up, you get higher energy levels. So this lowest energy state, n is equal to 1, is called the ground state of the atom. And energies, electrons in higher energy orbits, N2 or higher, are in the excited state. So these are the terminologies that Bohr's model proposed. So the higher energy states and the ground state. So here you can think of it as, for example, a ball falling down a set of stairs of different heights, different energy. So this would be the ground level, the lowest energy, and these would be the higher energy levels or the excited states. So Bohr's model was very important, again, because it introduced the idea of quantized energy states. That's what I really want to emphasize, is that Bohr's model used Planck's quantum hypothesis and suggested quantized energy states for electrons in an atom. But just like the model before it, like Rutherford's model of the atom, it was had its shortcomings, and it was just a useful stepping stone in the further development of our modern atomic model. So although Bohr's theory did a good job explaining the emission spectra of the hydrogen atom, so it did a good job explaining this one, the hydrogen atom emission spectrum, but it had its shortcoming in that it couldn't explain and make predictions about multi-electron atoms, and that these shortcomings then resulted in further investigations to try and further understand the behavior of atoms. So actually, it was becoming very obvious to many scientists during the first half of this 1900s that there was many key experiments that were not consistent with classical theories of light, and that this radical new approach was needed to look at the quantum behavior of the quantized behavior of electrons in the atomic model. So next, I just want to touch on the discovery of neutrons in 1932 by James Chadwick. And James Chadwick also won a Nobel Prize in 1935 for his discovery of the neutrons. He worked with Rutherford to determine the masses of the nuclei of different elements, and found that the observed masses of nuclei were not the same as the sum of the masses of the protons. So he concluded that a nucleus must contain not only positively charged electrons, but also something else, something neutral, something uncharged. And he called these uncharged particles the neutrons. So this showed that atoms can be broken down into smaller subatomic particles, and the discovery of neutrons. And here I have a table below that summarizes some of the key information about 3 subatomic particles that are most useful to us in chemistry and predicting the properties of atoms and matter. So these subatomic particles are the proton, the neutron, the electron. And I've just summarized, tabulated here that protons are positive. Their location is in the nucleus, and their relative mass is 1. So not their actual mass, but relative to other subatomic particles, they are assigned the relative mass of 1. Neutrons are neutral charge. They're not positive, they're not negative, they're neutral. Their location is also in the nucleus, and their relative mass is also 1. Now, electrons are negative, and they're supposed to orbit the nucleus, and their relative mass is much smaller. They're much, much lighter. They're about 1,800 times lighter than a proton or a neutron, and their actual weight was determined back in, where did I cover? Millikan here. So yeah, their actual weight is 9.1 times 10 to the minus 3 kilograms. That's the actual weight of electrons. They're very small, very light. So now from this, let's take a look at the periodic table. So in the periodic table, the elements are organized on this periodic table in horizontal rows called periods and vertical columns called groups. And the vertical columns called groups contain elements with similar properties. And elements arranged in order of increasing atomic number in the periodic table. And there's metals, which are shaded in the periodic table here on this particular periodic table. I have to say that there's many different representations of the periodic table containing different kinds of information. This one is just a very basic periodic table. So let's take a look at how you can retrieve some of the information about these subatomic particles from the periodic table. So the atomic number is the number of protons in the nucleus. This is called the atomic number. So here, let's take let me just copy this over here and we can talk about it on this slide. So in the periodic table, you will see that the atomic number is oftentimes shown right here above the element. For example, here we have potassium, number 19, atomic number 19, and it represents the number of protons in the nucleus. This number, this is what determines what is the atom. It's how many protons it has. Now, atoms are electrically neutral, therefore, however many protons you have, in this case 19, you would have an equal number of electrons in that atom. And we can look at an example. There's also the mass number, or the atomic weight. And this mass number is the sum of the number of protons plus the number of neutrons that an atom has. So for example, over here, if the potassium has 19, then if the atomic weight is 39, well, you just subtract the 2 and it will give you that it has 20 neutrons. So let's look at this example of oxygen. For example, Oxygen has an atomic number of 8. So here it is on the periodic table. Oxygen, number 8. And that 8 tells you that it has 8 protons in its nucleus. And just by virtue of it being a neutral atom, it must also have 8 electrons orbiting around the nucleus. Now, oxygen has a mass number of 16, which the mass number is the sum of the protons plus the neutrons. So from 16, the mass number, and 8, the atomic number, you can subtract the 2 and see that oxygen also contains 8 neutrons. So oxygen would have 8 protons, 8 electrons, and 8 neutrons. So that same example, we were looking at potassium. For example, you might be asked, determine the number of protons, neutrons, and electrons of a potassium element. So of the element potassium. So the atomic number of potassium is 19, as we said, and since the atomic number is equal to the number of protons and hence electrons, potassium would have 19 protons, 19 electrons, and the number of neutrons is this number minus 19. Now, some people call this 39, some people call it 40. It depends on which isotope of potassium you are looking at. So then, these are support questions. And if you remember when I was discussing support questions in the beginning of our lesson, support questions you don't have to hand in. It's not marked, but it really reinforces what was taught during the lesson. And it's strongly recommended that you work on these support questions and try and figure them out and answer them. So I want you, as a practice, try filling in this chart in your notes to complete the missing information and see if you can fill in every blank on this table. Fill in all the blank elements, the atomic numbers, mass numbers. So you would fill it across and up and down, fill it all in for the first 20 elements of the periodic table. So it's useful to still think about, even though the Bohr model is not completely correct, it still has its utility. And we can use these diagrams called Bohr diagrams or Bohr-Rutherford diagrams to still look at the arrangement of electrons and how they occupy, how are they arranged around the nucleus and the atom. So again, according to the Bohr model, electrons move around the nucleus in a circular path, and he called these orbits or shells, much like planets around the sun. Electrons in the Bohr model are supposed to be spinning so fast that their orbits seem to form a solid shell around the nucleus, and that electrons could not exist between these orbits, but could only move up or down from one orbit to another, from one allowed energy state to another allowed energy state, and that the electrons would be more stable when they are at a lower energy, so that's closer to the nucleus, as opposed to they would be in an excited state if they were at a higher energy that was farther away from the nucleus. And that each orbit had a maximum number of electrons that it was allowed to hold. So there was only a certain number of electrons that each orbit or each shell was allowed to occupy. So in the, In the Bohr model, the first orbit he called the K shell, and that orbit would only hold 2 electrons. In the second orbit, he called the L shell, it would hold 8 electrons. And in the third orbit, it would hold, it would hold 18, excuse me, and it would hold 32, so on and so on. So in Bohr models, each of these allowed orbits was assigned an integer n, and this was the quantum principal number, or the principal quantum number. And the larger the value of the n, the farther the electron would be from the nucleus. And the lowest energy would be n is equal to 1. This would be called the ground state of the atom, or this would be in the K shell, the first orbit. And then any of the other higher orbits, any of the other higher shells would be the excited states, where n would equal to 2 or 3 or higher. These would be the excited states. Now, how do we go about drawing a Bohr diagram or a Bohr-Rutherford diagram? So there's simple steps that you can follow using the periodic table. You can determine the number of protons, neutrons, and electrons for the elements. So you would refer to the periodic table and figure out these numbers for a certain element. For example, if you have to do one for carbon, if you're asked to draw the Bohr diagram for a carbon element, so you would follow the steps that are outlined here. So you would draw a circle to represent the nucleus of the atom. So you would draw a circle. And then you would write the number of protons and neutrons inside the circle. And then the electrons would be drawn in circular orbits around the nucleus, remembering that the lower orbits, the lower energy orbits would fill up first, and then you would move on to higher energy orbits. So let's do these steps for carbon. And we see that carbon has a mass number of 12 and an atomic number of 6. So we know it has 6 protons and 6 electrons. And then protons and neutrons is what make up the mass number. So take away 6 protons from 12, and it would also have 6 neutrons. So you would draw the nucleus, and you would draw 6 protons, and you write it as 6p plus, and 6 neutrons, 6n0 naught, to represent its no charge. And then you would start adding your electrons in the shells, starting with the first shell, the K shell holds 2 electrons. You would put 2 there. So remember, we've got 6 electrons that we need to fill up. And then the rest, the remaining 4 can go into the L shell. Now remember, the L shell can hold as many as 8 electrons. But in this case, we only need to put in 4 because that's all we have. It's 2 in the first shell, and the other 4 go in the next L shell, and that adds up to 6 electrons, essentially. Total 6 electrons. Let's look at another example. In this example, we're asked to draw a Bohr diagram for the element nitrogen. And so nitrogen has a mass number, atomic weight of 14, and it has an atomic number of 7. So that tells you that it should have 7 protons. So you draw your circle representing the nucleus, and you write 7 protons. The charge is positive, and the mass number is 14. So if you subtract 7 from there, you'll end up with 7 neutrons. So you write 7 neutrons in there. And then because nitrogen is neutral, all atoms are neutral, it must also have 7 electrons to cancel out the 7 positive protons in the nucleus. So 7 electrons. So starting at the lowest energy shell, we put 2 in there. And the next energy shell can hold up to 8. So we put the remaining 5 electrons in there. And this can be written in a shorthand way, like this. You can write your nitrogen and then 2 electrons in the first shell, and then 5 electrons in the next shell. And this is what we could probably use more frequently in this course. That's how we're going to use this shorthand way of representing the electrons in a Bohr diagram. So here we have another support question. You can draw the Bohr diagrams for the first 20 elements on the periodic table. And so atomic elements with atomic numbers 1 to 20, and then explain any patterns that you may observe based on the location of the elements on the periodic table. So these are 2 questions for you to attempt by yourself. This one and this one. You don't have to hand these in. And then here we have key questions. Now these are 4 key questions. And what I'm going to do for today's assignment, so there's 4 of you participating in this class. I think there's more students joining probably before the registration deadline, and they'll have some catching up to do. But for you 4, I think I'm going to assign each one of you to one of these questions so that you don't have to do all 4 questions. Each one of you is going to be assigned one of these questions. And what I want you to do is I want you to answer the question and present it in 2 days' time from now on Wednesday. Just talk about and show. If you want, you can share your screen to show your answer and talk about and how you went about answering these key questions. And for example, here you're asked to summarize using a labeled diagram in chart form the evolution of the atomic theory from Dalton to the Rutherford model. That's they're each worth 10 marks actually. So yeah, I'm going to assign each of you one of this. Another student will be assigned to explain what are the main weaknesses with the Rutherford model of the atom and how did Bohr address those weaknesses. So somebody could explain that, please. And another student would be asked to explain what is spectroscopy and how was spectroscopy useful in the development of the early atomic theory. And I'm going to ask another one of you to answer that. And finally, the 4th student in this course is going to be asked to talk about what part of the original model of the Bohr model still seems to be well supported by the experimental evidence, and to identify what was one of the weaknesses in Bohr's atomic theory.
Can I do 3? I'm sorry.
Yes, go ahead, Chidisa.
Can I do 3?
Sorry?
Can I do 3?
I'm just going to randomly hand it out. I don't think it's fair for any one person to pick.
Okay.
Okay, so I'm just going to randomly hand them out. But what I'm also going to do now, can someone tell me, did the school send out the PDF for the grade 12 Nelson chemistry textbook to the students registering in the course? Have any of you received an email containing that PDF file of the textbook?
Oh, let me check it.
No, I didn't.
Okay, so I'm going to find out how I can go ahead and make sure that you have access to the PDF of the chemistry textbook for this course so that you can look up relevant sections in that chemistry book. It's a great resource. It has very good explanations, and I've taken many of my material, many of my diagrams from that chemistry textbook. So I'm going to make sure you have access to that textbook so that you can go ahead and further read up on what is the best way to write up your answer to this question, to these questions. Each of you will only have to do one. So I just want to also take a moment to urge each of you not to copy answers either from each other or from the internet or from a book. I don't want to see any copying. Please go ahead, work together, form study groups. That is wonderful. That's a great way of learning, to work together and form study groups. But I don't want to see answers coming in that are identical for all 4 of you and on questions that are supposed to be individually answered. So for this assignment and moving forward, I really urge you to write your answers in your own words. Even if you're studying together, even if you all worked on a certain question and tried to figure it out together, that's perfect. But what you write in and what you hand in, please make sure it's in your own words. If I receive, for any of the assignments in this course, copied answers that are identical to either another student's or to a textbook answer or to an internet answer, I will automatically grade that answer as a 0. Now, instead of that, take a moment, read it, understand it, put it into your own words, even if it's not perfect English. I don't mind, I still can understand. Write it into your own words and you will at least get, if not perfect marks, partial marks, better than a 0. So I really, really urge you not to copy. A copied answer will get you nothing better than a 0. Write it in your own words and you will get a better mark. So yeah, it doesn't matter how perfectly worded somebody else's answer was, don't copy it. That's plagiarism. It's you won't learn anything by doing that, but it's also plagiarism, which in my course will get you a 0. But since this is a pre-university course, and I think most of you will be university bound, in university, plagiarism will get you expelled. And it's very serious and it'll get you into a whole lot of trouble. So I'm really, really looking out for you when I'm urging you not to plagiarize, not to copy answers word for word. Put it into your own words. It will sink in better into your own mind, putting it into your own words. Work together, but don't all copy the same answer, please. So, okay, so I'm just going to randomly assign so Borna, I'm assigning you question number 1. Judy, I'm going to assign you number 2, Sasan number 3, and Shadissa number 4. So each of you only needs to answer that one question. And then on Wednesday, we can talk about what's your answer. You can talk about it with your classmates, with me, and this will also give you a chance to explain what you learned.
Miss.
Yes. Yes, go ahead. I can't hear you. I think you might be having mic troubles.
Yeah, this is gonna be sent to Google Drive after the lesson, right?
Yes, after the lesson. So let me see. Did you have a Gmail address?
Yeah, I do.
You do. Okay, perfect. Yeah. So after the lesson, I'm going to share this this lesson here with you in a Google Drive. I'll send you the invitation, the share, and then also I'll send you an email. I'll email you a link to the recording of the lesson.
Okay.
And I'm going to try and make sure to make sure everybody in this course has a copy of the textbook, because that is a very important resource. Okay. So if you have any trouble afterwards accessing anything on the Google Drive, get in touch with me by email and I will take you step by step through it. I know sometimes some students were not able to do that. And once we went through it, they realized that it was there and they could easily access it. So yeah, if Judy and Shadissa, if you guys could immediately get yourself a Gmail address, share it with me, and then that way.
I already sent it to you, and also it's Shadisa, miss.
Okay, sorry, Shadissa?
Yes.
Shadissa, got it. If I'm not saying anybody else's name the proper way, please correct me. I will do my best. Shadissa. Doros?
Yeah.
from-
Now also I sent you the Gmail address.
You sent me the Gmail address? Okay, I'll have a look at it and perfect.
And for me, can I write it in the comments?
Just email. You have my email address. Just email it to me. That way I can just put you into my contacts.
Okay, perfect.
Okay, thank you so much. All right, so that takes care of that portion, that housekeeping. So I know we covered a lot in our first lesson of the atomic theory, and we will cover more in our second lesson. We will go more into quantum theory. So here I just wanted to make sure you understood that what we know about the atom and our understanding of an atom has changed a lot over many, many years, gone through many, many iterations. Many scientists have looked at it and come up with various models, starting from Dalton and his billiard ball model to J.J. Thomson and the raisin bun model. Then Robert Millikan figured out the mass of the electron. Ernest Rutherford proposed the planetary model of the atom and the idea of the nucleus. He discovered the nucleus, this very important gold foil experiment. Go ahead and read up more on it in your textbook if you need to. It's quite fascinating. This experiment is one that has actually stayed with me for many years since I was in grade 12. I remember this. My teacher actually showed a very funny comic, and I looked very hard to see if I could find that comic anywhere on the internet. I couldn't, but the results of this experiment, this gold foil experiment, were so shocking that it was as if, I think Thomson it was that said that it was as if you shot a cannon, a missile bullet at a tissue paper, and it bounced right back at you. That's how shocking it was. They fully expected it to go through as if, you know, a bullet would just go right through a thin sheet of tissue paper. But how shocked would you be if that bullet hit the tissue paper and bounced, came back right at you? And my chemistry teacher back then showed me a very funny cartoon of this, and it just stuck with me. I remember this experiment and these results very clearly all these years later. I wish I could have something funny like that to share with you, but just go ahead and read up more on it. So if you don't have any further questions, we can finish this class now. It's 7:30. If not, for the next half an hour, I'm still here and available. I can go through any of the other slides or any part of the atomic model that you wish me to repeat and go through again. Please don't hesitate to let me know.
I just have a small question.
Yes, Judy.
So for the work, do we have to send it to you, then discuss it for our next course, or do we just discuss it without sending it to you?
No,
The
send it,
answer.
yeah, send it to me, and then during class you will also talk about your answer with the rest of the class. You will explain what it was, and then we can all talk about it and add anything that we need to it. If anybody else has any other suggestions, if anybody has any questions, they can ask you or I can add to it. And this will just be a good exercise in presenting and also talking together as a class, which is not something you often get to do here. So let's yeah, let's use that as a good opportunity next class. Okay, so send it to me before the class next Wednesday, and then during class we will talk about it together, and each student will get a chance to share their answer. And okay.
Okay, thank you.
Yeah,
Okay.
no problem. You're welcome. I'm sorry, can you say that again? I couldn't hear you. Borna, I couldn't hear you. Can you repeat that, please?
Nothing, it's fine.
Okay, okay. All right. Okay, so I'm gonna stop this lesson now. I'm gonna share this lesson with you through Google Drive, and as soon as I have the recording, I will also share the recording with you. Okay. All right, everybody, have a good evening, and I'll see you again at 6 o'clock Wednesday. Okay, take care.
Okay, thank you. Have a good
Bye,
day.
miss.
No
Have a good
problem.
Thank you.
You too.
Bye.
Take care. Bye-bye.
Bye.